This is lecture 19 in network theory. So in this lecture we're going to discuss about the Laplace transform. So this Laplace transform is useful when we do RLC networks and when we have to find the response, either current response or voltage response, right? So before that, in the previous two lectures we have seen series RLC circuit with DC excitation, parallel RLC circuit with DC excitation. So in this lecture, what we need to remember mostly is one coefficient, that is zeta, which is R by 2 root of C by L. In this case, in the parallel 1 by 2 r root of L by C, or one more parameter we can remember like this: R by 2L whole square. It should be either greater than or equal to or less than something, right? 1 by LC. And in this also 1 by 2 RC whole square greater than or equal to 1 by LC. It is can be equal to or less than also, right? For critical damp, under damp, etc. Then what is the time constant in parallel and series RLC circuit? In series it is 2L by R. In parallel it is 2RC. Similarly, omega n is same in both cases and omega d is same in both cases, but zeta here is R by 2 root of C by L, and here zeta is 1 by 2 r root of L by C. And again we need to remember the D1, D2, the roots in series RLC. So these roots are R by minus R by 2L plus or minus root of R by 2L whole square minus 1 by LC. In parallel RLC, so these roots are D1 comma D2, it is minus 1 by 2 RC plus or minus root of 1 by 2 RC square minus 1 by LC. So this some concepts we have seen in the previous lecture. Now we will see two problems on this, right? Now we need to find the current response in the circuit shown. So this current response is in this loop, that is I of t. Now to solve this one, first we will see which it is in underdamped or overdamped, etc. We know the condition, that is R by 2L, either it is greater than or less than 1 by LC, so the whole square. So what is R? It is 4 by 2 into 1. So it is square means 4. And what is 1 by LC? 1 by L, 1 into 2, it is 1 by 2, right? So what is this? R by 2L whole square is greater than 1 by LC, or in another way, zeta is equal to 1 by R by 2 root of C by L. What is R? 4 by 2 root of C is 2 by 1. So this is 2 root 2. This is zeta. Again zeta is greater than 1. So in both cases it is overdamped system, overdamped response or overdamped system. That means the D1 comma D2 roots are in real roots, or we can say, what are the roots? We can say minus R by 2L plus or minus root of R by 2L whole square minus 1 by LC. So what is minus R by 2? Minus 4 by 2 into 1 plus or minus root of 4 by 2 whole square minus 1 by 1 into 2. So what is this? Minus 2 plus or minus root of, so 2 square 4, 4 minus 1 by 2, 3.5, right? Now, so one root is minus 2 plus root 3.5, minus 2 minus root 3.5. Now if I write the current response, I of t is equal to some a into e power minus 2 plus root of 3.5 into t plus b into e power minus 2 minus root of 3.5 into t. So this is the current response. So this is how to find the response. If they have given some initial conditions, so we can find this a and b also, right? Now if I take the same question in parallel RLC, so this is 4 ohm, this is 1 Henry and 1 Farad. So we will see the conditions. Again in this case we need to consider 1 by 2 RC whole square and 1 by LC. So what is this? 1 by 2 into R4 into 1 whole square, 1 by 1 into 1. So it is what 1 by 2 into 4, 2 into r into c, it is 1 by 16 square, and this is 1. So obviously it is less than 1 by LC, or other way, zeta is equal to 1 by 2r root of L by C. What is this? 1 by 2 into r is 4 and root of L by C. L by C is what? 1 by 1. So it's nothing but 1 by 8, or we can say 0.125. So that is zeta is less than 1, or 1 by 2r is whole square is less than 1. So it is underdamped system, or we will get underdamped response. The voltage response is underdamped response. Now to find this one, we know d1 comma d2 is minus 1 by 2rc plus or minus root of 1 by 2rc square minus 1 by lc. So minus 1 by 2 into 4 into 1 plus or minus root of 1 by 2 into 4 whole square minus 1. So it is nothing but minus 1 by 8 plus or minus root of, so 2 into 4, 8 square, so 8 square means 64, or minus 63 by 64, and it can be written like this: d1 comma d2 minus 1 by 8 plus or minus j root 63 by 8. So how to write the response? So this is the real part. So e power minus alpha t, that is minus 1 by 8 t into a cos beta t, that is root 63 by 8 t plus b sin root 63 by 8 t. So this is how to write the underdamped response. So it is always e power minus alpha t into a cos beta t plus b sin beta t, right? So this is about the RLC networks when we apply DC excitation. Now the important concept is Laplace transform. Now to find the given response, whatever we just now done, so we can use the Laplace transform approach also. Now what is the Laplace transform? If there is a x of t or v of t or I of t signals are there in time domain, when we take Laplace transform, so it will become capital X of s Laplace transform, capital V of s Laplace transform, capital I of s, right? Now how to find the Laplace transform? So the Laplace transform can be written like this: if it is a bilateral, it is minus infinity to infinity x of t into e power minus st dt. If this is for bilateral, so we will use generally for a network theory concept unilateral transform. So unilateral Laplace transform is x of s, it is only one sided, that is 0 to infinity x of t into e power minus st dt. So this is the Laplace transform we will use. Now we will see for resistance, for inductance, for capacitance one by one. But before that, we will find some basic signals, the Laplace transform, right? So what are those basic signals? So the first one is unit step signal. So suppose u of t is given, so what is the Laplace transform, right? So what is the units? So u of 0 to infinity 1 into e power minus st dt, right? What is this value? For integration of e power x, so e power x by differentiation of x, that is minus s, and the limits are 0 to infinity, so it will become 1 by s. Similarly for delta t, that is the unit impulse signal, so it is 0 to infinity delta t into e power minus st dt. So delta t minus t naught from the signal systems, delta t minus t naught is here 0, so this is x of t. If I substitute t naught here, we will get simply 1, right? So this is the impulse function property, that is minus infinity to infinity delta t minus t naught x of t dt means we will get x of t naught, right? So that is x of t naught means here t naught is 0, so you will get 1. Similarly, suppose e power minus at is there, right? Now what is the Laplace transform? 0 to infinity, because unilateral, e power minus at into e power minus st dt. Now if I take minus of s plus a common, then it will become t, and minus, if I differentiate, I will get minus of s plus a. So if I substitute the limits, I will get 1 by s plus a. That means whenever we see e power minus at, so when we take Laplace transform directly, it will become 1 by s plus a. Similarly, if I want e power at, so directly it will become s minus a. Similarly, sin omega t, what is the Laplace transform is omega by s square plus omega square. Similarly, cos omega t, I will get the Laplace transform as s by s square plus omega square. These are some basic signals under Laplace transform. Next we will see what are some properties, right, in a Laplace transform. The basic important properties are two, that is differentiation property and integration property, which are essential for the network theory problem. Remaining linearity, time shifting, etc., that we don't require here. So what is the differentiation property? Differentiation property, that is, if d by dt of x of t in time domain, so in Laplace domain it will become s into x of s minus x of 0 minus or 0 plus. Similarly, if this is a square, that is d square dt by dx square dx d square x of t by dt square. So that is Laplace transform is s square into x of s minus s into x of 0 minus x dash of 0 minus and so on. For the cube, we'll get s cube into x of s minus s into x of 0 minus s square into then s into x dash of 0 minus x double dash of 0, etc. So this is the differentiation property. Similarly, what is the integration property? Suppose there is an integration x of t dt, right? Now if I want the Laplace transform of this signal, so what is the, we will get x of s by s plus minus infinity to 0 minus x of t into dt by s. So this is generally we call initial value, right? So this is the integration property. So if I take the Laplace transform of integration of x of t, it will become x of s by s plus integration of minus infinity to 0 minus x of t into dt, or we can say simply initial value by the s. So these two properties are very important. That is, suppose there is a resistance R, right? So in Laplace, this is in time domain, the Laplace domain also it is R only, because V is equal to I into R. So in Laplace domain also, so it is V of s is equal to I of s into R. But if I take inductor and capacitor, it will change, because V is equal to L into di by dt, right? So what is this? It will become L into s I of s minus I of 0 minus or 0 plus. So it will become SL I of s minus L into I of 0 minus, right? Similarly, for a capacitor C, what is I? I is equal to C into dV by dt. So R V is equal to 1 by C integral I dt, because here we have found the voltage, so V is equal to 1 by C, so it will become I of s by Cs, right, plus I of 0 minus by S, right? So this is 1 by C, so integration, so it will, we can get I of 0 minus by C into S, right? So 1 by C is common, so integration of this one. So this is the inductor equivalent in S domain, and this is the capacitor equivalent in S domain. So now we will see That is the transient. Suppose if I want to do the transient concepts using the Laplace domain, then it is very easy. See, suppose if I take an inductor, right, and this is V and this is I. So how to represent in the Laplace domain if it is having an initial current of I of 0 minus. So first I will write V is equal to L into di by dt. So this is L into S into I of S minus I of 0 minus. So what is this? Ls I of S minus I of 0 minus into L. So this can be represented like this. So this is equivalent to one inductor which is SL, and here I of S is flowing, and there is a voltage source which is minus plus because this is a minus. So L into I of 0 minus. So for transient circuit in inductor can be replaced using S domain as like this, and this can be equal. See, this is a impedance and this is a voltage source. This can be represented by Nortons also. This will become SL and the current direction is downward. So current is equal to V by SL. So L into I of 0 minus by SL. So LL cancel, it will become I of 0 minus by S. So whenever there is a parallel RL circuit is given, so we will use this form. Where there is a series, we will use this form. Similarly, for capacitor, how to represent using Laplace domain? This is C, V, and this is I, right? So what is I or what is V? So if I write a loop, so V is equal to 1 by C integral I dt. So what is 1 by C? So 1 by C into integration property, that is 1 by S into I of S plus I of 0 minus by S, right? Now if I take this one, this will become I of S by CS plus I of 0 minus by C into S, or we can say this I of 0 minus by S as voltage, initial voltage. So this is can be written like this: I of S by CS plus V of 0 minus or 0 plus by S. Now what is the equivalent model? So it can be equal like this: a capacitor and there is a voltage source which is plus minus V of 0 minus by S, and this is the impedance as 1 by CS, and this is I of S and this is V of S, and this also can be written like this: parallelly 1 by CS and there is a current which is going upward, so V by Z, so that is V of 0 minus S by S. So this current voltage source V of 0 minus by S by 1 by CS, right? Or we can say C into V of 0 minus. So these are the two equivalent models in Laplace domain for capacitor. Similarly, these two are the equivalent models in for the inductor. Now I'll solve one problem on this, how to solve a transient question using Laplace approach, Laplace domain approach. Suppose there is a cube is given, there is a 10 volt source, right, and there is 1 ohm, and there is a capacitor switch, and this is position 1 and this is position 2, and there is a 3 ohm resistor, and there is a one more capacitor, that is 3 farad, and here we'll have 6 farad capacitance, right? So we need to find the current response in this, right? And this switch is moving from position 1 to position 2 at t equal to 0. So we can use the transient approach, RC network, simple, then we can find this I of t. This same circuit can be solved by the Laplace domain approach. First we will find at t equal to 0 minus or t less than 0 to find the initial values. So it is 10 volt, this is 1 ohm, and whenever the capacitors reach its steady state, it will be V of 0 minus, right? Next, here anyway the capacitor will be open, so anyway here there is no connection, so this Vc of 0 minus is equal to 0. Alright, this 3 farad one, this is the 6 farad. So what is the voltage here? There is no drop, directly Vc of 0 minus is 10 volts. Now for t greater than 0, so the circuit will become like this: 6 farad, and it is having initial voltage as 10 volt, that is Vc of 0 minus, and here 3 ohms, here 3 farad with initial voltage as 0. So this is I of t. Now how to do? So this will be transformed into S domain, so that is 1 by Cs, that is 1 by 6s, and there is a voltage source plus minus V of 0 minus by S. So what is V of 0 minus? Is 10 by S. Then this is 3 ohms, and it is 1 by 3s. There is no voltage, so it will become short circuit. Now we will find as I of S. Now if I apply KVL across this loop, so what I will get? 10 by S is equal to 1 by 6s plus 1 by 3s into I of S plus 3 into I of S. Right? See, 1 by 6s into I of S, 1 by 3s into I of S plus 3 into I of S. Now if I take I of S common in this, so I of S, and there is 6s, the LCM, so 1 plus 2 plus, so this is 3, so 3 into so I will make like this, plus 3 into I of S is equal to 10 by S. Right? If I take again LCM, so it will become 3 plus 18s by 6s is equal to 10 by S. SS cancel, so I of S will become 60 by 18s plus 3. Now to make this is an S plus A form, then I can take 18 common, so it will become 60 by 18 by S plus 3 by 18, that is 1 by 6. So what is I of S? We got I of S, we got 60 by 18 by S plus 1 by 6. Now if I take inverse Laplace transform, now we know that e power minus at, so what is the Laplace transform? S plus a. So inverse means 1 for 1 by S plus a. What is the Laplace transform? Inverse Laplace transform, it is nothing but 60 by 18, so 6 10s 6 3s, so it is 10 by 3 e power minus at, that is 1 by 6 into t. So this is the I of t. So by this may also we can find the responses using Laplace transform approach. So this is a very important concept, and which is useful while doing the phasor diagram, phasor domain approach also. Now before concluding this session, this lecture, so what is the L can be represented by simply SL, and C can be replaced by 1 by CS. Now even in phasor domain, so this S can be replaced by J omega, so it will become J omega L, and it will become 1 by J omega C. Right? Now so this is about the inductor and capacitors, right? Now so one properties of this Laplace transform, so there is two more, that is one is initial value theorem and final value theorem. It's a very simple one. So initial value theorem means if I want to find limit t tends to 0 x of t, so it will become limit s tends to infinity s into x of s to find the initial value theorem. Similarly, what is the final value theorem? Final value theorem is limit, if I want to find limit t tends to infinity x of t value, it will become limit s tends to 0 s into x of s. Now remember, this initial value and final value is valid for only stable systems, right? So what do you mean by stable? If poles of any transfer function it lies in left half of S plane, then it is stable system. Even single pole is coming to the right, so it is unstable. So it is something like this, right? So it is unstable system, right? So for stable systems we can find the initial value and final value theorem. right? So this formula problems for initial value and final value theorem we'll see in the next lecture.